Well, good afternoon, everyone, and welcome to our presentation for the disability system for a small boat. Before we get started, I'll just introduce everyone. From right to left, we have Shannon Roy, Christian D'Amico, Andrew Metz, Danny Hingston, Logan Kalinowski, and I'm Michael Contenti. Our advisor for this project is Dr. Stewart. So just to give a little recap of our project. Essentially, our problem was that a kayak in rough water is susceptible to excessive rolling, which usually causes discomfort for kayakers. Now what this means is kayakers of essentially any generalization, so it could be anything from fishing to just casual use. So our solution to this is to build a portable kayak system that will limit this rolling. And we really think that this will be good for essentially any type of use, as I said. So especially given that we just built a sailing center, we think that would be a really good effective use for Roger Williams students in the area. And I know that personally, the kayak I used for this project, which I will show later, the person who I got it from actually uses it for fishing himself, so I definitely know that would be able to use.
We decided the best solution to this problem would be to use a tuned mass damper. A tuned mass damper is a system which reduces the amplitude of oscillation of the structure. You can see in the diagram that the tuned mass damper is attached to the top of the structure. The mass of the system is represented by M2, the damper is represented by C2, and the spring is represented by K2. We considered three different types of DMDs for this project. The first is a passive system. This has a fixed spring and damping, so it can only be used to reduce energy in one resonance frequency. The second type was a semi-active system, which added controls to the spring and damper, so it could be adjusted to different resonance frequencies. And the last was an active system, which replaces the spring and damper with an actuator, which gets feedback from the sensors to automatically adjust to whatever resonance frequency is needed for the system at the time.
So in the literature we performed, we found various uses of tuned mass dampers. Tuned mass dampers are in civil structures such as skyscrapers, such as the Taipei 101 as seen in the first visual. This is a passive pendulum damper, which relies on a mass swinging at a specific frequency to counteract the acceleration on the structure. Another form of a passive tuned mass damper is a tuned liquid column damper, as seen in the second visual. A tuned liquid column damper relies on the movement of the liquid in a U-shaped container to counteract the forces on the structure. The spring force in the tuned liquid column damper is the difference in height of liquid in the container, and the damping is the result of the liquid traveling through an orifice located at the bottom of the container. And the downside of a passive system is that it cannot be adjusted during operation, which would require an external power source and sensing and a controller. So a semi-active system that we found was a semi-active tuned liquid column damper, shown in the third example, and this relies on a variable control valve to adjust the size of the orifice that the liquid travels through to inherently adjust the damping of the system. And another example of an active system we found that was actually fixed in the boat hulls was the Seakeeper, as seen in the last visual. And this is an extremely expensive active gyroscopic damping system starting at about $22,000, which is definitely not feasible for our project. But this system relies on a flywheel in a vacuum container fixed into the boat's hull, which spins at a really high frequency, and that creates an angular momentum to create a torque to the system. So this will create a force of the torque to stabilize the structure so that waves hitting the boat. The active support of the system will allow the tilt of the gyro so that the active support of the structure will tilt the gyro so that it will provide a wide range of torque at various sea states. And based on these technologies, it guided our design concepts, which were also based on customer needs.
So earlier on this semester, we sent out a survey through the ASME email, which was asking just a bunch of people what they would think about for a system to stabilize a kayak and what needs that they think would be relevant to the system and what they would like to see in the system, including costs and things like that. So the first thing that I would like to, from those surveys actually, we came up with these needs and all the different categories. And we also came up with a category of importance, which is on a scale of 1 to 5, 1 being, not so important, 5 being incredibly important. And we use the results of the surveys and then also our personal opinions on things that we would need and how important they would be to come up with these values. So the first thing I'd like to talk about is the ability to stabilize a kayak. We gave that a 5 because, that's like the core of our project. So if it's not able to stabilize a kayak very well, then there's no point in really doing it for this project. Another one is low cost. So most of the surveys said that they wanted to be under about $100, which is what we're shooting for the cost of this. And so we gave that a 5 as well, because that's pretty much the main thing that everybody hit on in the surveys. Another one is the effect on the kayak speed. So we didn't want to mess with the speed at all of the kayak, because we wanted to keep the experience of kayaking as similar as we can to without the system, other than, you know, hopefully it would just be a smoother ride and not gonna tip back and forth as much. And then another one is, I'll talk about why we gave this one a 2, is because we were hoping to design for more of a durable device. So for it to be easily accessed and maintained, while that is important, and if something breaks, it does need to be fixed, we're hoping that it will be more durable and that won't be too much of a problem. So we gave it a 2.
Alright, so we decided the best way for us to come up with a bunch of different solutions was to split up and do it individually. This way we wouldn't have interference from other people's ideas, so we would be able to have the most diverse set of solutions to choose from. After getting together as a group, we saw that some of our concepts had similar or the same components, so we combined them into the same idea. Then ultimately we had 6 different concepts that we put through our concept selection matrix, 3 of which stood out in particular. The first one was the mass along a track. This is an active system which uses feedback from sensors to push to drive the linear actuator, moving it to move the mass along with the kayak, changing the center of mass of the system. The second one was a telescoping tuned liquid column damper using telescoping PVC. Telescoping PVC is a set of interlocking PVC pipes that we could use in the system to fit it to different kayak widths. And this is an active system because it uses feedback from sensors to drive a 2-direction pump to dampen the system. And the third one was also a tuned liquid column damper using telescoping PVC. However, this one was only semi-active because instead of using a pump to drive the damping, it controls the position of the valve, which then would change how the liquid damps the system.
So in order to decide which design we wanted to move forward with, we developed a concept selection matrix. As Andrew mentioned before, we have the needs and the importances, which are from the surveys at the beginning of the semester. We rated these on a scale of 1 to 5, with 1 being the worst, 5 being the best. So I'll go through 3 of the designs here, pros and cons. The first one is the semi-active telescoping system. The pro of this system is that the telescoping PVC allows for it to be adjusted to fit into different size kayaks. One of the cons of this system is that it has to be manually adjusted by the user, which is too much work, which we don't want. The second one is the telescoping pump, which is an active system, which means the user doesn't have to adjust anything, and it automatically adjusts. One of the negatives of this system, though, is that the pump has to be a 2-way pump, which is too much work for us this semester. And the third and final design, this is the one we're going to move forward with, is the tuned mass damper on a track. That image right there is the initial design. We've since tweaked it a little bit, as you'll see in the SolidWorks. One of the benefits of this is the ability to automatically adjust without the user having to do anything. But of course, there is a negative, which is the mass of the system. This system is a little bit heavier than a couple of the other ones we've talked about because it has a mass attached to it, but that's something we're going to try to minimize as we move forward.
But so in the first slide, I had a picture of the kayak. We might have it later. I can't remember. So for the kayak testing that what we did, it has a picture of essentially it's like a hard to describe. It's like a pipe going across the kayak that went out of the water. So what we did for that was we actually inserted a mass into the end of the tube. It would have been hard to see anyway, but it was essentially acting as a moment arm, which we then used to determine the natural frequency after using the equation omega d over, and it's equals 1 over t, and t is the period. The period which we determined was 0.89 seconds. So how the experiment actually worked was we actually had Dr. Stewart in the boat to begin with, but after a little bit of testing, we realized that it was too difficult to do without someone that's not a neutral mass, because when people are actually in kayaks, they tend to balance it themselves. So realistically, it's not a good way to measure it. So what the picture shows we did to finalize that result was we just essentially grabbed whatever was on the ground and put it in there to use as a mass. And this actually worked a lot better because the mass was not resisting the rolling of the boat. So the biggest takeaways from that were that we determined the natural frequency, as I said. We determined the rolling motion of the boat, which is essentially just the rigidity of it. So some of the positives from that were like what I just said with our results, but the negatives from that experiment was that we forgot to consider the center of mass, because with the neutral weights that we added, we did not consider the center of mass properly. So as you can tell, like as a person is sitting in the boat, the center of mass could be a lot higher, but in the picture it showed that the mass was all below like the top of the boat, so it obviously would not be the exact same results. But either way, we still intend to revisit that eventually, with considering the center of mass. Yes, now onto this slide. So that was a little bit about the physical aspect of it, but here's some of the digital aspect that we focused on. So we split into two teams. One of them was a design team, and the other one was a project and simulation team. A programming team, sorry. And the design team focused on SolidWorks modeling, which we'll get into a bit later. And we essentially modeled the kayak as close to as a general kayak would be. And what we did was we inserted our chosen design into the kayak where we intend to place it. And now the simulation team, they actually coded and plotted the passive example for a two-mass dampener. Now the reason we did this is because it's actually the easiest way to do it. The passive example is a lot easier to code than a semi-active or active system, but really we just wanted to give ourselves a baseline for what we were trying to accomplish in the future.
Alright, so the winning design from this concept selection matrix was the TMD on a track option. You can see in the top image that the motor directly drives the pinion gear against the rack, sliding the device back and forth along the guide rails. Now, extra weight not shown in the image, such as batteries for the motor, would also be mounted on the platform with the motor. Now, this design is slightly different than the preliminary drawing for the mass on a track, but we had to make those necessary changes to reduce the different types of motion going on, and it just made the controls portion of this project much easier. And you can see in the second image that the placement of the device would be within the kayak behind the rider at the lowest point.
Identification and SolidWorks model, we were able to determine parameters of the kayak to analyze MATLAB. And its equation at the top, the terms in the red box represent the motion of the kayak. And this first term is the overturning moment. The second term is the stiffness due to the displacement of water. And the third term is damping. So within these terms, I is inertia, M is mass, R is the moment arm, K is stiffness, and D is damping, and theta and its derivatives are the rotation of the kayak. So we found the inertia of a sitting person in our literature as shown by the picture on the right. And because a sitting person, the center of gravity is different than a standing person, so we have to look into that a little bit more. And we determined the natural frequency of the kayak during our system identification as an set, and the inertia of the kayak was found using the mass properties of the kayak in SolidWorks. And using the equation for natural frequency, which is the square root of stiffness over inertia, we were able to determine the stiffness of the kayak. And so these are a set of second order ordinary differential equations which model a passive TMD. And the first equation is the same as on the previous slide, but this time the red box focuses on the TMD terms rather than on the kayak. So in this, the first term is the spring moment, the second term is the damping, and the third term is the overturning. So in these terms, x and its derivatives represent the linear movement of the TMD. And the mass of the TMD was set to be 10% of the mass of the kayak that the person sitting in. And the inertia, the natural frequency of the kayak was set equal to the natural frequency of the TMD to find the stiffness of the TMD. And the second equation up there represents equal and opposite forces on the kayak. And although our system is an active system, it was helpful to model the system using passive equations, which these are, because it is easier to model a passive system than an active system, and it helped us to determine how much support would be needed by the boat.
So to simulate the suppression of the rolling motion of the boat, a pre-decay test was performed in MATLAB. So this modeled the dampening of a kayak with and without the addition of the two-mass damper. So the two previous equations were coded into MATLAB, and the displacement of the system in radians was plotted over time in seconds. That can be seen in the first plot of rotational system response with and without the addition of the TMD. So we've seen that with the addition of the two-mass damper, the system is nearly damped out after about 4 seconds. So to determine the force output of the system, the spring force and the mass force and the damping force of the system were added together. And this would be the force that would be required of the motor to replace the spring and dampener of the system. And as seen in the second plot with the force in newtons over the time in seconds, the maximum force is about 100 newtons. So going forward, we would like to put the differential equations into Simulink to create an active damping system that would limit the error of the rolling motion of the boat.
So now looking at the budget, everything on this list is things that we know that we need going forward into next semester. We're hoping to order them at the beginning of next semester so we can start the manufacturing process. A couple things on this list, like the kayak, our estimated prices. We have it at $200, which of course if you're buying a new kayak, you can probably find one for more than that. But we're hoping to buy one used or even borrow one if we know we're not going to damage it. A couple of the other things like the motor driver, and the drill battery are also high-end estimates. We need to do a little bit more calculations, simulations in SolidWorks and Simulink before we can get actual numbers for those.
So moving forward into next semester, these are kind of our goals for the semester. None of the dates are set in stone yet. They're just kind of like placeholders as an idea of where we want to be around those dates, so those can change, except for the conference that I don't think is going to change. So by early February, we want to have a finalized list of parts and materials for everything that we're going to need for the semester and start our work with the controls in Simulink. So we're going to start working with Simulink and getting the controls to a basic point to be added into the system. And then a little bit after that, we're going to purchase all the parts, and then we can begin prototyping once the parts get here, which hopefully will be as soon as possible. And once we have a prototype built and ready to be tested with, we're going to incorporate the control system into that and start testing with a fully functioning, not a fully functioning system, but a system to get it to be a fully functioning system, which we hope to have done by the Eastern College's Science Conference, but that's up in the air. Only time will tell. There's possible issues that can arise and maybe slow us down. But that's planned for next semester. So some of the challenges that we've hit so far are that we found it's difficult for a person to act as dead weight to get accurate numbers, and because they just tend to naturally damp out. So if the kayak tips this way, the person's going to tip this way just out of instinct to not fall out of the boat. Another issue is that if the system is tuned to one person and then another person gets in, that's going to change the entire weight of the system and how everything's going to react. So we need more complicated controls to be able to identify that itself and adjust whenever the person gets in, changes the system. Another one is that the center of gravity would also change with people. So, if a tall guy like Logan were to sit in the boat, his center of gravity is going to be a little bit higher. If a shorter person gets in, it's going to be lower, so that will also change how the system works. And thank you for listening. Do you have any questions?
It's been a while since I've done vibrations and dynamic systems, so bear with me. So you talk about the challenge of getting the live person to behave as dead weight, right? But when they're actually kayaking, they're going to behave as live weight, right? So it sounds like you're simulating and you're programming and you're tuning around dead weight. What's going to happen when the user is also, instinctively reacting, but then the tune mass damper is as well?
So ideally, the system is, since it'll be active, it'll be able to fight against any force like leaning over and things like that. So we want to also try to possibly market it towards like fishermen. So if they're off one edge of it and there's just a constant force going, like tipping the boat this way, it'll be able to provide that constant force back and keep the boat as stable as possible. So hopefully it would be able to counteract them if they overcorrect, and if they do just minimal changes, it might not kick in. Like there would be a certain threshold to where if there's little bitty waves, you don't want things slamming back and forth and moving the kayak. So there'd be a certain threshold to meet before it would actually kick in and
move it back.
So, since I know you guys were planning for prototyping or testing this like to be German, have you thought about like if you're testing it and it's more trait form, it's really pulled out, and like in the bay, and then
So we thought about making some sort of test stand out of wood, talked about that. Not sure how easy it is to simulate water. So we're gonna try to talk possibly to people at the rec center, maybe use a pool, because obviously we can't really use the bay because 30 degrees out, that would be fun. So possibly the pool, maybe a test stand of some sort.
Question. It's kind of an interesting problem because just by virtue of adding your TMD to the kayak, you've changed the system properties, right? So, when you compare like with and without the TMD, are you comparing it with the TMD there just as a dead weight? Or are you comparing it with the kayak without the dead weight? Like when you did your, force or whatever, looking, I think it was the Dambu curve.
It was with and without.
So the one that included the TMD included it actively damping out, and the one without, did it include the boat with the mass of the TMD just doing nothing?
Yeah.
Okay. Is it makes for an interesting problem, right, because we talked about boat stability and motion engineering, so, the location really matters too, where you put it, so have you thought about how to place your TMD to maximize the stability without even having to turn on the TMD at all? Like, where would you put it and how would you get it in its maximal location?
I guess we'd have to create a stability curve of some sort
Yeah.
to find the center of buoyancy in the center of gravity of the system.
Where would the best place be for it?
Well, practically it would be like directly, where the most space is, would be like directly behind where the person's sitting. That's where we actually inserted into the model that we had earlier, so that's probably the best bet practically.
Practically, right, but then does that guarantee that you get more stability or would you get less stability?
Well, it would probably be better to include the center rather than on one of the ends. So yeah, that's more towards the center.
Or even really thinking more vertically about it, right, and trying to drive down where your center of mass is, and so I think that becomes a big challenge in this because Mike brings up this point of like practically what can you do? Really you want to drive it down as far as you can, but kayaks are just pretty flat bottomed, and so I think that presents another interesting challenge to try and build a TMD that can really actually sit at the very bottom of your boat if possible, which is not easy to do, but would add so much stability without even having to press on, which is cool. Something to think about.
Kayak have a, what we call it in sailboat, a big mobile mast that's down
Yeah.
underwater, right? That you'd have to be adjustable for different depths of water that you're in, things.
That was actually in our concept selection, was adding essentially that.
Look around that weight
Yeah,
as well.
right.
The deeper you go, the less weight you need for, but anyway. Could you go back to the slide where you had the plot of the vibration damping out? So your time scale is like seconds. What I was wondering about, and I haven't wrapped my head around it completely, so your motor working on the rack and pinion is going back and forth, right? And I'm just thinking to produce this, how fast is the motor going linearly? And then based on that, what's the acceleration that we're requiring from the motor shaft? And you're going back and forth, right? And so I was just thinking about, I don't know the answer, I don't know motors well enough to have an intuitive sense of like, is that gonna be a challenge or not? It seemed like if it was a really fast frequency system, like that motor has to be zipping around, and that could be a challenge, and just accelerating its own mass, right? It's just another thing. But if it's a fairly slow period, then maybe it's okay, and it can just, and then I was also wondering if there were other, and I'm not necessarily asking for the answer, I'm just talking out loud, other potential ways to drive it, you know, could you do a ball screw that's gonna be pulling a mass back and forth? I don't know if that would be better. Yeah, anyway. That wasn't really a question. Something I was thinking about for you. Other questions? Steve?
If you put the mass in the back of the boat, is the mass that you're thinking is gonna be, how much does it weigh?
So we're aiming at around 10% of the weight of the kayak and the average rider of the kayak. And the placement of the kayak would be ideally like as close to the rider at the lowest point within the kayak that we need, because that allows it to be the widest spot of the kayak, so it would give us more room to move the mast back and forth.
If, with the mass in the back of the boat, is it a weight that's big enough that would affect the, kind of how the kayak sits in the water, whether or not the front's in the air, or if it's gonna still sit flat in the water?
And ideally, since it'll be very close behind the rider, it won't change the center of mass too much in terms of the length of the kayak.
Could you flip to your budget slide again? Is the drill battery powering the motor? And have you done any estimation yet of how much energy you need, how much power
So,
you need?
one of the issues we've run into is selecting a motor, because there's a lot of factors going into what we need, because it needs to be able to move back and forth relatively quickly, but also be able to provide that torque. So it's been kind of a struggle to find a motor, and a lot of the motors we've been looking at have had varying power requirements. And we figure drill batteries are relatively cheap, easy to charge, and can provide a larger amount of power in case we need that larger amount.
I'm just thinking, kind of similar to what the bike team was doing in terms of how long is the trip, how frequently is the system running, and how much, and blah, blah, blah. How big does that battery need to be? Power tool motors are, I think, things like that. Good performance power must
So, looking at the pictures you got, this is a system that goes inside the shell of the kayak, right? Okay, so then how do you plan to mount it inside the kayak? And then you talked about wanting like minimal like adjustments with it, right? Because you guys don't want the riders going in and messing with it. So then in terms of powering it, how do you plan on, if your battery dies, replacing it or charging it, or making sure that your system constantly working with something you have to run inside the kayak and then cover so that it's not getting hit by the water every time you leave it?
Or anything, you can just take that out without having to take out the whole system if the battery dies.
Part of the system is that we'll have most of the weight on top of that like flat moving piece. So everything would be relatively easy to access. So you can just grab the motor and unplug it or not the motor, sorry, the battery, and charge it. And if it does end up just being a drill battery, that would be easy for us. I'm sure we would, if it were to be a legitimate product, we would probably adapt it to be something more easily chargeable. And we would probably just have to have some sort of encasement for it to worry about waterproofing.
And then the follow-up I had to that is, it's something we considered on whether or not this is something that comes with every new bike or something you attach yourself. So is you guys designing something that the everyday user can attach to their own kayak, or something that comes with every new kayak?
Plan to be attached,
Okay.
like aftermarket.
Okay.
All right, let's thank,